Hello again, this is Mr. Smith with reading quiz number 2. This reading quiz focuses on the relationship between limits and infinity. And just a quick note, as with reading quiz number 1, we'll leave discussion of the limit laws for class. This PowerPoint just focuses on the more algebraic connections between limits and infinity. Some quick definitions. We have an infinite limit if any of the following is true. The limit as x goes to a either from the left or the right of f of x equals positive infinity or negative infinity. If the limit is equal to positive infinity, we say the function increases without bound. If the limit is negative infinity, the function decreases without bound. We have a limit at infinity if either of the following are true. The limit as x goes to infinity of f of x is equal to L, or the limit as x goes to negative infinity of f of x is equal to L. Alright, and it's important to make a distinction between a limit at infinity and an infinite limit. An infinite limit has an answer of infinity, while a limit at infinity has the x value go to positive or negative infinity. So when we're evaluating these limits, one thing that will help us is our knowledge of basic functions. For polynomial functions, the polynomial's end behavior matches the end behavior of its highest degree, just like we talked about in pre-calculus. So, for example, the limit as x goes to infinity of x to the n is equal to infinity no matter what the n is, as long as it's an integer. Now, this could change if we put a negative out in front of the polynomial, but the basic framework is that the limit goes to infinity. For example, limit as x goes to infinity of x squared is infinity. The limit as x goes to negative infinity of x to the n is a little more complicated and depends on whether n is even or odd. If n is even, then we get a situation where the polynomial goes to positive infinity on both sides of the number line, as x goes to negative infinity and as x goes to positive infinity. If n is odd, then we get a situation where the limit as x goes to negative infinity goes to negative infinity. So for example, limit as x goes to negative infinity of x to the fifth would be negative infinity. For basic exponential functions, you have to consider that one side goes to infinity, while the other side has a horizontal asymptote, as we see in the graph off to the right here. For example, limit as x goes to negative infinity of 2 to the x is equal to 0. And if you consider the graph of this exponential, you'll see why. As we go to negative infinity, the exponential levels off to 0, and the limit as x goes to positive infinity of 2 to the x will go towards positive infinity. Some ground rules. If we have a function that is a ratio or a rational function, that's where things get interesting. What we have to consider is which part dominates, the numerator or the denominator. We'll look at more complicated magnitude comparisons in a little bit, but for now we'll just consider 3 variations of polynomials. First one, if the highest degrees of the numerator and denominator match, the limit as x goes to negative infinity and as x goes to positive infinity both equal the ratio of the coefficients on those highest degrees, and we'll see that in example 4. If the denominator has a higher degree than the numerator, then the limit as x goes to negative infinity and as x goes to positive infinity both are 0, which we'll see in example 5. And if the numerator has a higher degree than the denominator, then the behavior of the rational function is equivalent to the behavior of what happens when the numerator and denominator are divided, which we can see in example 6. So let's take a look at those examples. Example 4, limit as x goes to infinity of 5x to the 8th minus 7 over 6 plus 4x to the 8th. You'll notice that the highest degree in the numerator is x to the 8th, and the highest degree in the denominator is x to the 8th, with a coefficient of 5 on the top and 4 on the bottom. When we divide out and cancel, as we'll talk about in class, we'll see that the coefficient ratio of 5 to 4 is the value of the limit as x goes to infinity. The degree of the numerator and denominator were the same in this situation, which is why we got that answer. In example 5, we evaluate the limit as x goes to infinity of 7x to the 8th minus 1 over 3 plus 10x to the 9th. The degree of x to the 9th overpowers the degree of x to the 8th in the numerator, and so we end up with a limit of 0. The degree of the denominator is larger than the degree of the numerator. Finally, in example 6, we did the limit as x goes to infinity of 6x to the 8th minus 1 over 3 plus 2x cubed. The degree on the top is x to the 8th. The degree in the denominator is x cubed. When we cancel this out, we see that this rational function will act similarly to 3x to the 5th when we divide out the degrees on the top and the bottom. Well, the limit as x goes to infinity of 3x to the 5th, as we saw in the previous slide, will end up being positive infinity. Limit as x goes to negative infinity of the same function, 6x to the 8th minus 1 over 3 plus 2x cubed, is going to be the same as the limit as x goes to negative infinity of 3x to the 5th, and that limit is going to be negative infinity. Remember the previous slide, that odd polynomials will go to negative infinity as x goes to negative infinity. Notice that the degree of the numerator is higher than the degree of the denominator in this case. The difference of degrees, which is an odd number, helps tell us what polynomial end behavior we need to compare the rational function to. Some special cases. We get some special cases when we use absolute value in square root. First, note that we define absolute value of x to be positive x when x is bigger than or equal to 0, and negative x when x is less than 0. And the square root of x squared is absolute value by definition. So, if we wanted to evaluate the limit as x goes to infinity of 2 times the absolute value of x minus 3 over x plus 4, we notice that absolute value of x is equal to x for x bigger than or equal to 0, which we are when we're going to positive infinity. So this is the same as the limit as x goes to infinity of 2x minus 3 over x plus 4, and that limit is 2. But if we were to go to negative infinity, that limit as x goes to negative infinity of 2 times the absolute value of x minus 3 over x plus 4, the 2 times absolute value of x will go to negative 2x, since absolute value of x is negative x for x less than 0. So the overall limit will end up being negative 2. You get two different limits going to different infinities. A same problem arises when we do limit as x goes to infinity of the square root of 7x squared minus x over x minus 1, and the same function as x goes to negative infinity. First, as we say above, we note that the square root of x squared is equal to x when x is positive and 0, and square root of x squared is negative x when x is less than 0. Thus, the limit as x goes to infinity of square root of 7x squared minus x over x minus 1 will go to positive x times square root of 7 over x, since x is bigger than or equal to 0. And so that overall limit as x goes to infinity will be positive root 7. But we get negative root 7 when x is less than 0, and we go to negative infinity with our limit, because, as we see above, square root of x squared is equal to negative x when x is less than 0, which takes place right here. Relative magnitude of functions. What happens if we involve a ratio without polynomials, or with things in addition to polynomials? As x goes to infinity, we have a bit of a pecking order, and we got some nicknames to help us out here. So the most important function, the most powerful function, is what we call our power tower, x to the x to the x to the x, and so on, which we rarely use, but I thought we'd include it. The function x to the x, exponentials, which we'll call ninjas. One example is 3 to the x. And it's important to note that 3 to the x is what we'll call a third degree ninja, which is more powerful than 2 to the x, which we'll call a second degree ninja. We got our polynomials, which we'll call pirates. Again, x cubed is more powerful than x squared because it's a third degree pirate as opposed to second degree. We've got logarithms, which are called our lumberjacks. And then, of course, we got sine and cosine, which, just like Tar Heel fans, go up and down depending on the success of their team. So, the application of the power tower. An example from the reading. Limit as x goes to infinity of 7 minus x to the 4th over x cubed plus 2 to the x. Notice we've got multiple combatants in this battle, and we always need to look at who the best fighter is. Even though the numerator has a very strong 4th degree pirate, the denominator has a much stronger second degree ninja. Since the ninja's on the bottom, the limit is equal to 0. In this example, we have 2 7th degree ninjas on the top fighting 3 7th degree ninjas on the bottom, with a couple of constants and an 8th degree polynomial thrown in, a pirate. Since the ninjas overtake any pirates or constants, the limit as x goes to infinity of this function will be just the ratio of the ninjas that we have fighting, the 7th degree ninjas, which will be 2/3. Now, we just did limits as x goes to infinity, but what happens about limits as x goes to negative infinity? Well, most of the same rules apply, except for an important thing. Ninjas can't travel backwards in time. They lose their power completely. This is because limit as x goes to negative infinity of 2 to the x, or any other normal exponential, will just be 0, as we talked about earlier. In addition, lumberjacks or natural log functions won't exist at all, which certainly affects the limit, and the limit would not exist immediately. Thus, limit as x goes to negative infinity of 5 plus 2 to the x over 7 minus 2 to the x would be the same as limit as x goes to negative infinity of 5 over 7, because the two ninjas, 2nd degree ninjas, will lose their power. So this limit overall will just be 5/7. If we want to evaluate limit as x goes to negative infinity of x cubed plus 5 to the x over x squared minus 2 to the x, then we notice again the ninjas fade no matter how powerful they are. This is the same as limit as x goes to negative infinity of x cubed over x squared, and that limit goes to negative infinity because the ratio of the two polynomial functions is just x, and limit as x goes to negative infinity of x is negative infinity. Quick example to go over from the guided practice. Limit as x goes to infinity of 4x to the 4th plus 5 over x squared minus 2 over times 2x minus 1 squared. Notice that the degree of the denominator is not easily found, but we don't have to completely distribute. That would be wasting your time. We just notice that the highest degree of the first factor is an x squared, whereas if we were to FOIL this second factor out, we would get 4x squared as the highest degree there. Thus, the highest term in the denominator would be 4x to the 4th. Now, knowing that, we can compare our numerator and denominator to find that they have the same degree. Thus, the limit will be the same as limit as x goes to infinity of 4x to the 4th over 4x to the 4th, which is just 1.